Okay, welcome back to NATS 1945A. We are talking about Chapter 4, Nuclei and Radioactivity. The learning goals of these chapters are, we want to know what a nuclei is, what is radioactivity, want to know why some nucleuses are stable, and what is the binding energy and how this is related to property of the nucleus and the stability of the nucleus. We also want to learn a little about the statistics of the nuclear decays, want to know what is alpha decay, beta decay, gamma decay, and how we can make sense of all of these. Okay, now if you remember previously, we talked about the size of the atom. Atom is the smallest element in the universe with the same chemical properties, but atoms are not the smallest fundamental particles in the universe. You can break an atom into several different particles, including electrons and protons and neutrons. In general, you can say protons and neutrons are concentrated at the center of the atom in its structure called nucleus. 99.9% of the mass of the atom is in the nucleus. And the nucleus is almost 10 to the power of 15 times smaller than the atom. Now, in a simple scaling, you can take the solar system and scale it in such that the entire sun is like a basketball with diameter of with a radius of about 30 centimeters, or the diameter of the 30 centimeters. Now, in that scaling model, when you put the sun as big as a basketball, then Pluto, which is the furthest object in our solar system, would be about 2.6 kilometers away from Sun. In the same scale, if you take, for example, gold atom and you scale it up to the size of a basketball, about 30 centimeters, then you will see that the electron from the outermost layers of energy would be about 5.3 kilometers away from the nucleus. So nucleus is incredibly small, an atom is incredibly dense in the nucleus, and it's filled with an empty space between electron and the nucleus. Now, there are some models explaining how the nucleus and the electrons are interacting with each other. In general, we are going to stick with the classical models where it assumes that the electrons are particles rotating in circles around the nucleus, and the protons and neutrons are basically point-like particles in the middle of the nucleus. Now, in reality, quantum mechanics since 1925 is teaching us that electrons are not like particles. They are actually more complicated than particles, and they can be instead of rotating in a circle around the nucleus, they might have a much more complicated structures. But this solar system model of the nucleus and the atoms, the Bohr model, is good enough for us, and we are going to use it and continue. Okay. Now, in the language of size, you might say that the largest microscopic object in a micrometer size is a virus with the size of about 10 to the minus 7 meters, about 0.1 micron. Then smaller than that, you will have molecules of the order of 1 nanometers. Then atoms will be about 10 times smaller than molecules with size 10 to the minus 10 meters. Nucleus, which is at the center of the atom, would be about 10 to the power of minus 15 meters. And protons and neutrons, which are the constituents of the nucleus, will also be made of other elements. So inside a nucleus, you will have protons and neutrons with a size of 10 to the power of minus 15. And then each proton is made of perhaps some other fundamental particles. We call them quarks. Now, neutron is a little heavier than proton by about 0.3%, but almost the same size. And protons and neutrons together each one, is about 2,000 times heavier than electron. Electron is very light, so the majority of the mass of the nucleus is inside protons and neutrons. Electrons are so tiny you can ignore them when we talk about the masses. Now, some people claim that there should be some other internal structures inside these quarks, like the strings, but we are not going to deal with them, and so we ignore them for now. Okay, now there is a terminology we have to use, and so we want to make sure that this terminology is understood properly. The first question is, the nucleus, we refer to it as when there is one single nucleus, and one single nucleus might have plenty of protons and neutrons, but still we call it a nucleus. If you have two nucleus, then we use the word nuclei. So the plural of the nucleus is nuclei. Now, a nucleus is defined by the number of protons of that nucleus. A nuclear species is defined, or sometimes they call it nuclei, as a species, a nucleus, with some specific number of protons and neutrons. So if you have two protons and let's say two neutrons, you will have one nuclide. But if you have two protons and one neutron, then you have a different kind of nuclei. Even though the number of protons are exactly the same, and the number of protons is going to define what kind of element you have, but still there are different kind of nuclei. So this is helium, for example, 4, and this one is helium 3. Both of them are helium, both of them have two protons, but now the number of neutrons are different. So these become different nuclei. Now, the number of electrons and the number of protons in a neutral atom is exactly equal. So when we talk about a neutral atom, we are talking about the number of electrons and the number of protons. When they are equal, then the atom is not electrically charged. If you have more electrons than the protons, then you're negatively charged. If you have less electron than the number of protons, then again you have an ion which is positively charged. But when you have a neutral atom, then this atom is electrically neutral with equal number of electrons and protons. In general, a nuclide with a symbol or element E is defined with this terminology. You will have, let's say, hydrogen, so this becomes the element E. The label is hydrogen, H. If it's helium, then the label would be He. If it's iron, then it would be Fe, and so on. There is 3 numbers here, which we want to refer to them as important numbers for this atomic symbols. N refers to the number of neutrons. Z is referred to the number of protons. We sometimes refer to it as atomic number. And then A is the sum of the number of neutrons and the number of protons, which is referred to as mass number. Assuming that neutrons and protons, or each one has 1 unit mass, then the mass number is technically the total numbers of protons and neutrons. By the way, neutrons and protons are together referred to as nucleons. So a nucleon is either a neutron or a proton. The mass number would be the number of protons and the number of neutrons all together. And the atomic number would be the number of protons in a nuclide. So a neutron and a proton, each one is referred to as a nucleon in general. It's like boys and girls, but it's, again, at the end, each one is a person, regardless of their gender. So it's an easy way to talk about the protons and neutrons, regardless of which one we are referring to. A proton is positively charged. A neutron is neutral, so it has no electric charge. An electron is negatively charged. There's also something called isotopes. When the number of neutrons in a nuclide is different, even though the atomic number is the same, they have the same element, but now they have a different mass number. So these are referred to as isotopes. For example, this element E has the same number of protons, Z, but now the number of neutrons are different, N1, N2, and N3. And so as a result, the mass number is different. So here's carbon. So this is referred to as carbon 12. It has six protons, 6 neutrons, and the mass number is 12. This one is referred to as carbon 13. So the mass number is 13, but the number of protons, Z, is 6, the number of neutrons is 7, and the total, the number of protons and neutrons together, is 13. This is called carbon 14, which has 6 protons, 8 neutrons, and the total number of nucleons is 14. Now, when you look at a chemical table, you will see a symbol like this. So this becomes the symbol of the element. So C stands for carbon. Here you have the number of protons, or the atomic number. The number of electrons here is mentioned when the atom is neutral. So it has a 2 and a 4 together, 6 electron. So it's neutral atom, so the number of protons and the number of electrons are technically equal. Now, here down here gives you a number which is not an integer. So it's not really the atomic mass number. What this is here is literally the average atomic mass number. And the reason we have a non-integer atomic mass, average atomic mass, is because, well, carbon comes in a variety of different isotopes. You can have a carbon, we can have a carbon with 3 neutrons, or 4, or 5, or 6, or 7, or 8, or 9, or 10. Not all of them are stable. Only the one with 6 neutrons and 7 neutrons are stable. Hence, carbon 12 and carbon 13. And you can see here the natural abundance of these two elements are non-zero. Everything else is 0. So naturally, you cannot find carbon 16, you cannot find carbon 9 in the nature, but you can find 98.9% of time carbon 12. And only 1.1% of time is carbon 13, with a half-life which is infinite. That means they are stable. They live around forever. Now, carbon 14, as you can see here, there is very little of it around, and it has a half-life of 5,730 years. That means if you have some number of carbons, let's say 100 particles, after 5,730 years, half of it is decaying to carbon 12, which is a stable, and half of them remains carbon 14, which is radioactive. We'll come back to this one later. But the whole point of this idea here is, how do we get this non-integer average atomic mass? Well, you take this number, which is the natural abundance, you multiply it by the mass in units of atomic mass, and then you add it to the other abundance multiplied by the atomic mass of that isotopes. And then you add them together and you normalize it by dividing by 100 to get that number. You're not supposed to do the calculation, but just where this number comes from, why this one is not exactly 12, 6 protons, 6 neutrons. It's because this is not exactly the number of protons and neutrons. It's not the atomic mass, rather it is the average atomic mass number. Okay, now I talked about atomic mass unit. We don't measure the mass of a carbon in units of kilogram or gram because they're extremely tiny and they're extremely light. And so what people have done is they have invented another way to measure the mass of these fundamental elements. We call it atomic mass unit. We use symbol AMU, sometimes people use U or Dalton even. And it means that one atomic mass unit is equal to 1.660540 very precise, times 10 to the power of minus 27 kilogram. Now, in a practical sense, what we do is we know that 22.4 liters of any gas, let's say you have carbon-12 in the form of gas, at temperature 0 and at pressure which is 1 atmosphere, very close to, let's say, sea level, which this is referred to as 1 mole, we know that 1 mole of any gas would have this amount of particles in it. So if it's carbon, then it has 6.02 times 10 to the power of 23 atoms of carbon in it. This was discovered by Avogadro, and so we refer to it as Avogadro number. If you measure the mass of 1 mole of carbon, which has 6.02 times 10 to the power of 23 atoms in it, then the mass of that 1 mole of carbon would be exactly 12 grams. Okay? And because we know that carbon has 6 protons and 6 neutrons together, so if you divide it by 12, then you would get technically 1 atomic mass of 1 mole of this element to be 1 gram. Okay? So in general, you would say that the mass of the carbon-12 would be 12 times the atomic mass unit, where the atomic mass unit is technically defined now precisely to be this number. Okay, so now you may think that why did we use carbon? I mean, before carbon, people used different kind of elements to define the atomic mass number, but because carbon is very easy to purify, it's one of the most abundant element in the nature, and you can easily burn a little tiny wood and create pure carbon. It's very easy to create 1 mole of carbon-12 and then measure its mass. And so eventually people replaced any other definitions for the atomic mass with definitions by the carbon-12. So there are some questions provided to you on eClass. Now it's time for you to take those questions.